Hello, and thank you for joining me here today with Data Science Teacher Brandyn. And we're getting to the cool stuff in NLP. I guess all those kind of more basic models, I guess you would say, although we got quite advanced, are good kind of because we'll add to these more advanced models that we'll be studying, transformers, and we'll add kind of some of the advanced things that we practiced on top of them to really make them kind of start to work well. So we're still going to work with this is still or these transformers at a simple level. We're starting off a little bit simpler in this class today, uh, and they're still a little bit tricky to work with, but they're not so bad. And so DistilBERT is the simplest version of the BERT. It's distilled down from the original BERT. To use this though, we're going to need to import the transformers library. Here's the right transformers. Okay. It doesn't come automatically with Encode, so you have to install it every time, but it's not so bad. To inspect the data, we're going to use the word cloud, but we're going to import word cloud, so capital W word cloud. We're going to import TensorFlow as TF. We're going to import TensorFlow.cares or import layers, okay, with an S here. And then we also import label encoder and train test split. Okay. And so we're going to import, I ended up not using NLTK. I use NLTK to remove stop words normally, and so I did try it with and without. And I have the code, we're not going to do it today, but I have the code for that. The reason I didn't use it, actually, the stop words with an LSTM, they overcomplicate things for the LSTM, but they don't really still work that great, if we're honest. BERTs, these more advanced models require, and then into GPT require the more advanced, require the stop words. It actually helps if they need a context for the words and stuff. Okay. So here we're going to take out some of the punctuation though today. So import all of those, and then we'll import the financial news from my GitHub reservoir. Back and then check for null values. Okay, so importing, oops, going too fast. Okay, so checking for null values, no null values today, and then we're going to inspect the labels. Look at the back and inspect the labels. Okay, and so we're going to, I gotta spell this correctly, look at the back end. And so what we're going to do is we're going to put the ploly into the back end of our pandas plotting function. So pd.options.plotting backend. So basically very simple, but it changes now pandas plot. We don't really have to do too much differently, but now we'll automatically plot using Plotly instead, so we get a little bit more interactivity, which is just kind of nice little feature and stuff, and it helps in a little ways when we're inspecting things today. So it is better to do the specific plotting function instead of the general plot and then you go kind equals bar, kind equals whatever. It's better to use the plot dot and then bar, so the individual function for each plot, because then you get some of the built-in options in Plotly are just right in this plotting thing, this plotting function in the bar plot or the line plot, like right in the actual specific plotting function. And then you get a little bit more flexibility, a little bit more of the quality options are involved in that. So kind of small, but it's kind of nice. Now you can just inspect this. This really helps later on. We're looking at the plotting history and stuff. I find it's super nice for the plotting history. So what we'll do is we'll make everything lowercase like we normally do here. So str dot lower. And then what we're going to do here, so make it lower, and we're going to go str dot split. So this is really just so that we can inspect it for our word cloud. So str string dot split, and then what we're going to do is str dot split. And it's going to split on the space and put everything into a list. Nothing super fancy, but if we have a list, we can join it to this list. So we basically put it all into the basic one big long string of everything that we have. So we're going to turn text, and we're going to we start off with a space here, because what it's going to do is going to kind of iterate. So every time it iterates, it's going to go space, next word, space, next word, and the next word is next item in the list. Right? So it just keeps adding space, and then next word, space, next word, and so on and so on. So you get a nice little thing. Let's just go split dot join. Okay. The way that we make that magic happen is with the join function right there. Okay. Let's just run this, code split, and now we'll be able to put it all together into the word cloud. So we'll go none, capital W, word cloud. Okay, sorry, object or word cloud object. But then we're going to generate it from this text that we have, this big long thing of text. We're going to create a figure. So we do control the width and the height of the word cloud. That really does a lot more to control the pixels, like so many pixels, like the quality of the image. If we want to actually control how it displays it, we'll go figure and then put it on a fig size. We're going to go IM show. It's more of an image than it's just a it's just data. Okay. So we're going to go axis and we're going to turn those off. We're going to go tights underscore layout and pad 0, just make a really small edge. We don't really need an edge in this one, and a kind of class finished is show. Boom. We got some other things right here. So what we're going to do is background up here in our word cloud background color. Or I apologize, background color. Okay, so background color, and then what we want to do for our base color is set this to yeah, okay. I got confused by the none right there. Just so I use for my replacement items, use them, but we don't really want any other color than the base color. Color you can set it as black, I guess, but so we can inspect and really see what is the most common word that occurs, and we'll keep track of these. We'll use a word cloud to really inspect where our errors happen and how we can go about resampling, because really there's many ways that you improve BERT, but one of the big ways that you can help is by upsampling and downsampling the values. And I found that it worked out well this time as well. So just look at, if we break this down now by positive sediment, and we get our word cloud here for positive, neutral, and we can inspect kind of each one of these. And I can let you do that. Inspect each one of these by each one of the positive negatives, and all I'm doing here is taking a split when we're logically indexed by negative, neutral, or positive comments. So we can expect to kind of see which words are different for each group. Okay. So let's get into the pre-processing section. So one of the first things we'll do is we'll remove the punctuation. Okay. So there is, I mean, the best way to do this is we're going to make our own little function right here to apply this. Okay. So what we're going to do is str dot make trans. It's a big translator. It's going to fill the punctuation with nothing, right? So we'll just replace it with nothing. And so what we're going to do is, okay, now that we made the translator, what we're going to do is we're going to text dot translate, and we're going to give it our translator. So nothing too fancy, and we're going to put this into a function. We're going to return then our text without the punctuation. And what we're going to do is we'll then use pandas.apply, which is a fantastic function. And it's going to apply our function on our new story called feature. Okay, so this story. Okay, and so you can see we remove all of the punctuation. Okay. So let's go into this one. So here's the code to remove the stop words. Again, I actually didn't find it really worked well, so we won't do it today because it usually doesn't help with BERT. You might find that sometimes it does, and there might be certain situations that you want to. So I left the code so you can see it, but we're not going to do it today, so I didn't keep that. Okay. So I'm going to make my inputs and outputs. I think it's always a good idea. It's not, you can use X and Y if you want to. I think that's still pretty common. I find input and output just in my head is a little bit better way to set this up. Okay. So what we're going to do is we're going to do input, and I just removed the vowels, so nothing so much writing today. So it's input train, input test, TS, and then input, or sorry, output, which is OTPT, comma, TR, and then OTPT test. Okay. X test, X train, Y test, or sorry, Y train, Y test. Okay, so just keeping track of those, and it's a little bit longer than X and Y, I guess, but I find it's a little bit easier. It just helps me think through, because sometimes you start having multiple inputs, multiple outputs, and X1, X2, X3. It just kind of it works. If it works for you, it works. I find it doesn't work that great for me, and so I like to do something a little bit different. Okay. So one of the important things just to save our test data set, to save the train and test together, or sorry, the input and the output together. I'm just going to concat these. I'm going to save a df test for at the end of the workflow. And obviously, you don't always know this when you first start out, but I decided later on that I wanted to save this, and I came back up here and found a place to do it. Okay, make a list of my targets right here. So as we talked about, upsampling and downsampling are kind of one of the ways that you help train your model, which mistakes to make a lot of. I tried a way in a very simple way that we can give it more or really make it impartial to start. We're just going to give it some of each of the samples, so it should be a little bit more equal stated. And what we can do in this sense, when we do positive, neutral, or other, we're going to upsample certain amounts. And this side, we're going to do equal to start off to really give it the best chance. But this is a simple way for making lots of errors in 2 or 3. What we can do is we can give it some more samples of these to give it essentially better predictions to help it learn better and understand those certain situations. So what we're going to do is when it's a positive situation, what we're going to do is we're going to, so if it's a positive, so if the target is a C, so we're going to iterate through this list that we just created. And then what we're going to do is we're going to create ins, so indexes, and that's all we're doing right here. We're creating indexes, right? So nothing super special at this moment, but what we're going to do is we're going to have our inputs, our data frame, right? So it's one column, but input, we're going to select out the locations based on the input of our output, on the index of our output. So we do logical index on our output, and then just get the indexes from that, and then we're selecting the indexes from the trains. It's a little bit to follow. And then what we're going to do is we're going to sample those and get 1,400 samples. We don't really care about the samples at this moment. We do want those, but we want to be able to take them from the train and the test. So what we're going to do is we're going to sample 1,400, and we're just going to take the indexes when we sample it. So a lot happened there. We use the output to logically index, and then logically index itself, and then take the index values to sample the rows from the train that meets the positive in the output, and then we sample those, and then we just take the index of those. Okay, so it's a few things that happen there, but all happen one way, and really just to create a set of randomly generated index values that can be repeated. So sometimes we will have just bootstrap resampling with replacement, and then we're going to put the ins in our location and ins in our location function right here. Okay, we're going to select out our input temp and output temp. Okay, else if it is neutral, we're going to do the same thing. Here we're going to do n equals to 1,400, and we are going to replace the value, so we can sample some rows twice. And we're going to take the index value. In the third one, we're just going to do else in the third one. So it's not one of those other two, it has to be one of the other ones. So what we're going to do is take the index values right here. So we're going to logically index, and then we take the index values of that logically indexed series, I guess you would say, and we're going to take the index values to sample from the training input. So we use the output to sample from the training input. Take samples of that. We save those indexes so that we can sample both the train and the input and the output together. And we're just doing this for the train because we don't really want to upsample the data set as a whole, because we don't want any repeated rows that were in the training to be repeated in the test, because it's very easy to map and guess, but we want to be able to predict new articles and stuff, and that turns out to be quite a bit harder than, yeah, you can map and learn exactly what caused this, but it doesn't really turn out to be very good at predicting, and it turns out to be very easy to kind of overfit. So, and then here we go. So we have our train test split, and I'm realizing what I did wrong here. So I'm just looking at this just to show my mistake. So what I did here, I was talking while I was doing this, and I put series at the bottom here instead of what I should be doing is concat. So we want to concat these every time. It's kind of like the common thing with the dot append in the list. What I did here, I gotta make sure I'm paying attention to the code I'm writing while I'm talking. And this is a good reason that we put the data frames, the blank data frames, right at the beginning. So I'm going to restart this, and it's going to create the blank data frames again. Now we're going to concat, so we're going to keep putting these stuff back together instead of what we were doing before. We were just creating two series out of these. And that's why I was getting the weird too, but now you can see here, put train one, just like we would expect here, but we have new sample rows for each one of these. Okay. So I'm going to upsample false negative words. The way I created this was down here at the bottom when I looked at the false negatives right here. Okay, so false negatives, I found words in a word cloud. I'll show you how we got to this point later on, but I got up to, I found words, right? So I wrote down, these are the false negatives, these are the false negatives, these are words that appear a lot. And I collected words, just kind of 5 for each one of them, false negatives. And what I did was then, when I came up here, I have this list now. Now it did turn out to be 15 because some of them repeated. But what I did is I'm going to sample up those. This is very simple. It's kind of like the simplest way to do it. We're just going to look for sentences with these words in them, and we're going to upsample it when it is a 0 or a 1. So it's kind of maybe not doing it exactly perfectly. We should be a little bit more targeted. When it's 1, it's these. When it's 0, it's these. We're just going to upsampling everything to make this as simple as possible because it can get quite complicated. Okay, so we're going to create this list of false negative upsample words. And you can see here we have our data frame. We have our one data frame here. What we're going to do is we're going to add back in the output just to make our lives a little bit easier. So we'll access equals 1. And then next, now we have them kind of put back together. We're then going to go, as we upsample this, we're going to go dftrain.ilock is in, and we're going to put this into a list. Okay, so is in this list right here. And so this is a word. I mean, it's only one word, but just to get it to work with this is in function right here, we put it in a list. Okay, we're going to do quite a few things here. So we're logically indexing to make sure we're getting the rows of it being in the list. And then we're also going to do another kind of dual logic index. Just notice that there's two sets of, there's the purple and the blue. There's two sets of parentheses right here. And so for the first logic statement, we have, is it equal to negative, or is it equal to neutral? So for zeros and ones, we're going to double check this. Okay, we're going to sample these, and we're going to get a sample of 20% more. This is a little bit complicated. It's good. Sometimes you need that one line if statement, right? So I'm going to go, it's this 0.02 if the word is s, and then else if it's 0.5, because there turns out to be a lot of just s's, right? That has to do with removing the apostrophes. But there's lots of just s's, right? So else 5%, replace that. Okay. And then what we're going to do here is we're going to go pd dot concat. So we're going to upsample some, and we're going to take 20% of those and then just add it back into the data frame. And I forgot the syntax right here. ilock. It needs to be ilock, not obviously. Didn't see the blue there. You probably noticed that I was making a mistake. Oh, and I'm silly. Is in, I forgot, is in, so I did this one part right here incorrectly. It's dot, so we're going to take this value out, take this one thing, and we're going to say it is in, and we're going to check is in. or sorry, not is, string dot contains. Yeah, there we go. It's fun writing code on the spot. So here we got this string contains, and so everyone, just gonna go slow when you make mistakes. It doesn't seem right because I was thinking that made sense the first time when I wrote it, but it usually, when you go slow, sometimes you realize that that doesn't really make very much sense. Okay, so here I left the code. I found this and I experimented and I tried this upsampling or downsampling the false positives count when you over predict on certain words. It didn't help in this situation, in this simple way that I did upsampling. So didn't help in this situation, so we're not going to do it today, but I did leave the code just to kind of show if you wanted to try and kind of experiment with different words. I only used again, I just chose 5 words of the mistakes for each one of the mistakes, and you could probably choose a lot more and you'd probably get a lot better. Well, hope I might get a lot better output. Okay, so there we go. We upsample our words right here, and we can see now we've been adding this many rows. So we still got quite a few ones with just S, euro, or percentage. We've got quite a few extra rows here. And so now we have a total of 8,200. Okay, so we're going to do that. Our DF train, we're going to go. So what we want to do to remake our input and our output, we're going to just use iLog. We're going to sample from the first column, which is our news article, and our second column, column number 1, we're gonna take our, which is our positive, negative, just our values, okay, or our classes for our target. Okay, and so if we look at those now, we have the right shape. They're both the same size, which is important. And just to double check there. So really important with Bert. This is very different than an LST model. This is not something you would need to do. What we need to do here is we need to add CLS tag and SEP tag at the beginning and the end. This is specifically made for Bert to work well. So this is not something that you need to do, but this is how Bert works. This is a very specific thing to do, but it will still do predictions without this, but you will find it increase when I tried it without it. And it made like a 0.15% increase in the accuracy just doing these simple things. Okay? Something they don't really tell you in school, And so here what we're going to do is you're going to do, so we want to do square brackets. And do square brackets and just CLS, all capital letters. And we're going to do a sentence. Sentence. And then we're going to do square brackets, SP for sentence in input train. So we're iterating through the input train and we're taking the sentence and we're just putting before and afterwards the second. We want to just actually put a space at the beginning right here and a space and right here right after close and a space before. Just make sure there's a space in between those. Because we use that to create the tokens, that space. Okay. And then we're going to do the same thing here. So we're going to go CLS space plus sentence. Space, square brackets, SEP. Okay. For sentence in input test. So we're going to train and test again. So just remaking those and just adding the tags before and after. Okay, so nothing super, you can't really see it afterwards, but it's there. Okay, so here we're going to use the tokenizer. We're going to use the auto tokenizer from transformers. Stick with that. Okay, so we're going to do auto tokenizer, and we're going to go from, when we call it down below, from underscore pre-train. Okay, so we're going to do the DistilBERT-base-uncased. So there's no case here with this one, so we'll import it first. Tokenizer. Okay, so when we use this, what we're going to do is we're going to go, okay, so when we go to after we initialize our tokenizer, our BERT, our auto tokenizer from the DistilBERT-base-case, we're going to go tokenizer in this function, token dot tokenize, and then for sequence in that. So it's going to go through every sequence and then just essentially just separate the words on white spaces. That's kind of what we call tokens in NLP. You're really just talking about individual words, okay, to make it simple, to not make it sound super fancy. So we're going to tokenize both of those. Okay, so it's really just, and that's not good enough yet for a model. But if we take a look at this, see, we have our tag and then each word separated by comma. So it's a list now. Okay, and we see a square bracket on the outside to confirm that. Then what we're going to do is we're going to go Tokenizer, and then convert tokens to and I'm not sure why I left this there. A little bit cheating. I think that's just some extra code right there. But so Tokenizer to convert tokens to IDs. We're gonna do the same thing. So Tokenizer. To IDs. Okay, so there we go. We're gonna run that, and you see now we have our IDs created, which is a number value for each token for each word. Okay, you can see here the tag is 100101, and well, this is 102 on the other side right there. Okay. Okay, so getting into the next section, we're going to look at using just TensorFlow to quickly find out the number of words. I was interested in the number of words in this data set. So we're just going to use kind of a more classic workflow that we've seen many times before. So from Keras, from tf.keras.preprocessing.text capital T tokenizers. We're going to import the TensorFlow tokenizer, and then we're going to go tf.bit it on text with an S there, on text, and then if we go tokenizer.word index, get the word index. Okay, so this is a little bit easier to get this from classic tensor, and if we want to know how many vocabulary words we had, individual words, we could just get the length of this word index, and so we have 11,000 words today, which is quite a bit. Okay. Getting the max length of our rows is kind of important. I'm actually going to say that we don't use this time. This is a good way to kind of set it a little bit more organically, but it's also a good understanding to have how big, I guess you would say, or how diverse the range of your texts are. So here we're going to do max text, and we get the length of each sequence. So we get the max of the list of the lengths of each sequence for the sequences in our inputs, right? And through each row, getting the length, and then getting the max input. Okay, so you can see here we have, and this is sometimes, so with this data set, it changes quite a bit. Sometimes it's 76, sometimes it's 110. Because there are not many that are very large, I set the maximum at 80. I do this manually so that every time it's always, the data is always pre-processed the same way for as I'm reloading up models that I have trained before. This is a little bit easier to kind of keep this all the same. Okay. So what I'm going to do next, I'm going to do tf dot keras dot tills dot add underscore sequence. Okay. And then from the next one, so we'll do that same thing here. tf dot keras dot utils dot add underscore sequences. I forgot to set the max text. So just to make sure that we're using the one that I set up above, we're going to redo this just to set the size to be same as we set before. Okay, so just make sure we rerun the workflow. Okay, so you can see we have a shape of 80, We should go to 80 for both our train and text inputs. Okay. So we're going to convert our labels to numeric values so that we can use them in our neural network. Okay. So we're going to do this. We imported label and counter from the very beginning, at the very beginning. So we're going to, if you see our values as negative, neutral, positive, we need this to be label. We need those to be in the number form. Okay. Even for the pre-processing stuff that we're going to do. Okay. And then we're going to get the encoder and we're going to fit it on the text as we create as we initialize this output. Okay. And then we create LE, and then we're going to LE dot transform. Those. Okay. There we got that working properly. You can see we have 1400 positive, 2500 neutral, and 4000. Okay, so run our label encoder. And then what we want to do as well, I'm going to create at this moment the test. So we're going to use this later on in our inspections to look at our errors in our test set. We're going to put everything together right now. To make this work, we need to reset underscore index. From the original, they won't stick together properly. We just need to reset this. And we want to drop the index. We don't need to save that. We just want to reset it. And then we're going to put that together with the AND series for the outputs. Okay, because that has kind of just defaults. That's what I'm saying. So let's see that. So what we want to do is then do the output to categorical. So this is essentially one hot encoding. So tf.canvas dot details dot to underscore categorical. The next one, then we want to do our output, and we're going to do number of classes just to kind of just signify how many classes there are supposed to be, so to what to build. Okay, and then details, and then set gears. We're going to have an extra. We're going to fill that in, and then to underscore categorical. So now we wanted to take a look at this. We have one train. We're supposed to look at our test others for train, and look at we have one encoded target class. So this will now work with the linear algebra that our network will use to make this work. Okay, so let's get into the fun stuff. Well, it's all fun, but here what we're going to do is we're going to import our model that we're working with today. So from transformers, we're going to import TF, capital B, DistilBERT model. And then we're also going to import from initializers constant. So we're doing two things today. And what we want to do is here we want to do TF. So in our first time we're going to do our input. We're using the functional model today to set some parameters that we'll use right here in our hyperparameters, I guess you would say. It's just nice to have those organized up at the top. Here we have our input that we're going to take in. We're then going to do TF DistilBERT model. And we're going to go from pre-trained. In that one, we're going to go weights. So this is a TensorFlow object, so we want to get out just NumPy, so NumPy. So we need an embedding matrix, so we create a transformer layer. But we're going to use this today just to get the weights of the embedding matrix. So we're basically using first the DistilBERT to get an embedding matrix. This is going to train really, really fast. It's going to be really quite awesome. Okay. And this is, so once we got our embedding matrix, what we're going to do is in our embedding layer, we're going to do the embedding matrix shape 1, shape 2, and then we're going to go embedding underscore initialize. Embeddings initialize. And what we're going to do is we're going to give constant constant, we're going to give it our embedding matrix. And what we're going to say, kind of get a little cramped up here, but we're going to say trainable is set to false. And then in the next one, we're going to get started with our model. So we build our embedding matrix from our DistilBERT model, and then we're going to use kind of more classical, not classical, but kind of more typically we've done up until this level is use bidirectional layers with LSTM and a couple dense layers. Okay, so we're going to go tf dot keras dot layers dot bidirectional. In the bidirectional layer, what we're going to do is tf dot keras dot layers dot LSTM. And we're going to go to return, really important this one, return underscore sequences. Okay. It's important for this one. Okay, and it just keeps the extra dimension, which is super duper important for the next LSTM layer. Okay. So bidirectional again, and we're going to do a second LSTM layer here. And we're also going to return the sequences from the second one as well. Then after we come out of this, we're going to go global max. So global max pooling layer. We're then going to have a dropout layer. So dropout. We're then going to have a dense layer. We're going to have the activation. And it's good to have on to help prevent overfitting, which is really important, is to have the kernel regulate. Just noticing here, this is kind of helpful just seeing this red line here, just noticing right here, but it's actually a 1D, so it's global max pool 1 dimension. Usually you can call it that, I don't know if it's really 1 dimension. So here, just noticing I might have a spelling mistake in how I spelled this name right here. So yeah, there we go. So TF DistilBERT model right there. So just noticing, paying attention to where we have these red bars, it just makes our life easier. I'm certainly not perfect writing code, so drop out right here, make a dropout layer, and then we make a dense layer. We're going to do our activation is going to be the softmax, so we're going to get the biggest one of those. So we're going to go here, define our model. So this is the functional model. We're defining the inputs and the outputs. Now we have to tell the model, so tf dot keras dot model. Okay, so give the model the input. We're just giving a list. We only have one input in this situation, and there are outputs right there. Okay. So then in the next one, what we're going to do is compile the model. So model.compile. Our loss is categorical cross entropy. Our optimizer is that, and the metrics we want are just accuracy data. But it's asking metrics, it's asking for an X. Then so let's get this started, and we're going to make sure it's spelled compile right. So noticing it's not right there. Compile. That's it. Take a second to get that all loaded. I forgot to run the cell first. So make sure you run the hyperparameters first. Set the model. And so just some warnings. Maybe bias, spelled kernel ray QY. And an extra int. I don't know why I found an int. Spell kernel regular. You know, that's one of the arguments I see in speak Google to help me show results for kernel regulars. Regularizing. So just to show that. ULARIZ. It's a regularizer. A little bit tricky to spell for teacher Brandyn. Okay. English, I don't teach English, I teach data science, right? English is tough sometimes. Okay. So we're going to do our compile, but that's why we have the internet for when English doesn't work well. Okay, so we're going to fit our model. We're going to do our batch of 32. We're going to do our inputs, validation underscore data, and then we're going to do epochs. And we're going to train this for 9 because we really don't need that. Okay, so I should wait for this to train. Oh, and I made a mistake there just to make sure everything was working. So we've got batch size. Okay. Now see how fast this trains because we're just using the embeddings from the DistilBERT, and it gets us a pretty good score. But you'll see we'll be able to do better as we get to the more advanced, kind of the starting point for Bert. But we'll be able to kind of turn it up and do some more interesting things with it in the future. This is a very good introduction to, well, one of the ways to use Bert. And really, you'll see at the very bottom, I did an experiment with the LSTM one just to see. And it is considerably better, and I think one of the big things is you don't see this extreme overfitting that you see with the LSTM, where it's not possible for it to do better, essentially. Yeah, although we will see some overfitting. Just to be clear, it does overfit eventually at some point, but getting closer to the GPT type of model, which we'll get to eventually as well. Okay, we trained it. It only took 8 seconds for each epoch, which is very, very fast for the model to scale. You can see my experiments, and I was just playing with different things. I just thought it would be good to show kind of how I quickly rate these, because I have performed quite a bit to get it up to this level. I tried lots of different things and stuff, and so this just shows the last several ones. I left them just to show kind of what it looks like. I just noticed when I was training my model, I saved it as an H. So what I'm going to do here in the pd.data frame, I'm going to go h.history, and I'm going to plot. And because we did at the very top, we did this in Plotly, or with the Plotly engine. It really just allows you to inspect this training history, which I find to be quite valuable. You can really look at the exact accuracy, the exact loss, and stuff. Gives you an extra ability to train this. So I'm going to do I'm saving this right here as well. I'm saving it as the upsample one because I did the upsampling that we saw. But I say I have a model from before that I did before I did the upsampling. So just to show us how that works, I'm going to do, so we're going to predict from a model that we just trained. So we'll get to that. So we're going to tf.math.confusion matrix. And then we're going to tf dot, just remember it's in one hot encoded our outputs. So what we need to do is we need to convert those to the index value of which one of the columns is predicted to be highest, and that will give us our, so we want to make sure that we do the argmax across the row, so axis equals 1, and then we're going to do that for our predictions and our original, our true values. So tf dot argmax. Axis here. Okay, so really good. We're then going to put this into a heat map, and we're going to note this equals true, and we'll set up here. We'll set axis equals set underscore title. Okay, so like that. So we look at our predictions right here. These are again really fast predictions as well. Set title, so not titles, title. Oh, English. Okay. And we'll do predictions for our test and get the same thing here for our. So just to show our error analysis, to show up the way that we loaded up our model. This is it's a little bit different than you would expect to do. Okay. So we're going to do tf.carrots.utils.custom object scope. Okay, so you just have to kind of know that you're importing the TensorFlow model with the underlying Hugging Face transformer. So just because it needs to know that this is not all a TensorFlow model, right? So what we're going to do is we're going to say with tf.carrots.utils.custom object scope, we're going to go So we're going to use this df.dis, so our model that we imported before, and we're just going to use that to open our model. Okay, so we're going to open this with tf.keras.models.load. Okay. Apologize. Load models. I'm putting a lot of S's on the end of my stuff today. Load model right here. So again, we're using the TF DistilBERT to give context to where our model is and the layers that we have in it. So it's just because it's a little bit more advanced, we have to kind of load it up in a slightly more advanced way, but it's nothing, again, once you know how to do it, it's not super complicated. Figuring it out the first time is certainly tricky and challenging sometimes, but loading it up is not so bad. So this is loading up the original model, not the upsample data that I did for this final model, just the model. You can see we did get very good predictions, but it was making some mistakes, making less mistakes than what we'll see in our final model. And this is a very simple look at how we can do the predictions. So just again, getting predictions, putting the predictions back into the data frame. So we have our our true values and our predictions. Okay? So we're going to do our columns and just looking at sort of true predictions. So making those. I'm going to make these into word clouds then, just like we had up above. Not going to really, not who we've done this already. We don't have to spend more time on this. And making a word cloud. So just to show what I did here, right? So we make our word cloud based on the times that it is either true or false. Okay? So what we're going to do, so you get the news stories here based on when it was a 0 and it was actually a 1. So our false negatives, right? So it's going to be in the bottom left quadrant. If we were to look at the confusion matrix, is when we make a mistake here, false negatives are this kind of quadrant. We predict a 0 and it was actually a 1. We predict a 1 and it was actually a 2, or a 0 and it was actually, I don't know, 2 or something like that. So these are the mistakes that we make, right? So we predicted 0 and it was actually a 2. So this is the false negatives, and these are the ones that I upsampled this. This region over here would be the false positives, where I predicted a 2 and it was actually a 1. So I kind of over predicted, I guess you would say. Here's the false positive. And so we go through that. So I made a list of these short numbers, just kind of looking, kind of chose 5. You probably upsample a lot more like that and give it a little bit more context, but upsampled those. I then downsampled as well. I found that that didn't help our predictions. It didn't really hurt them, but it didn't make a difference. So I decided not to do it because there's no real reason. But now you can show this upsampling is a really important technique for BERT to get it to train better and with a complicated network. So we still use it in a very simple way, but I hope you enjoyed our first iteration of the BERT model using Hugging Faces and TensorFlow. So thank you very much for joining me, and I will see you next time.